All right, today we're diving into the incredible science behind high-temperature superconductors. And trust me, this is a technology that could literally change everything about how we power our world. I mean, just think about that for a second. No resistance, no traffic jams, no energy wasted as heat, just a perfect, seamless flow of power from point A to point B. Well, that's the wild promise of superconductivity, and we're about to break down how scientists are turning that dream into a reality. Okay, so here's the key difference you need to get. In a normal conductor, like the copper wires in your house, electrons are constantly bumping into stuff. It creates resistance, an electrical traffic jam, and a ton of energy gets lost as heat. But in a superconductor, that resistance drops to absolutely zero. It becomes a flawless, frictionless highway for electricity. But for most of history, this perfect electrical highway came with a huge catch. A really, really chilling problem that kept it locked away in only the most advanced labs on Earth. So, the whole story really kicks off with a simple element: mercury, way back in 1911. Scientists discovered that if you cooled it way, way down, its electrical resistance just poof, vanished. It was a massive discovery, but it had one giant limitation. And that limitation was the temperature. Mercury only became a superconductor at an absurdly low 4.2 Kelvin. To put that in perspective for you, 4.2 Kelvin is just a few degrees above absolute zero, the coldest temperature that can possibly exist. We're talking negative 269 degrees Celsius. To get something that cold, you need liquid helium, which is super expensive and rare. So for any practical purposes, forget about it. This was the deep freeze problem. But then, in the 1980s, something completely unexpected happened. A total breakthrough from a totally different field, kicking off a ceramic revolution that changed the entire game. And this revolution gave us what we now call high-temperature superconductors. Now, let's be clear. High temperature is a pretty relative term here. We're still talking very cold. But compared to nearly absolute zero, it's a whole new world. And what's so wild is that the breakthrough didn't come from a simple metal like mercury. Nope. It came from these complex, brittle ceramic compounds, specifically one known as YbCO, that's yttrium barium copper oxide, a totally new class of material for the job. And this new ceramic, it hits superconductivity at temperatures above 77 Kelvin. Now that might not sound like a big jump from 4.2 K, but in the world of physics, this was a monumental leap. So why is 77 K the magic number? What's the big deal? Well, it's the boiling point of liquid nitrogen. All of a sudden, you could achieve superconductivity using a coolant that's as common as air and way, way cheaper than liquid helium. This was the single biggest step in taking superconductors from a lab curiosity to a potentially practical technology. So how in the world do these ceramics pull this off? Well, their secret superpower, the key to the whole thing, comes down to one crucial element: oxygen. You see, these YbCO ceramics have a special crystal structure called a perovskite. And the really cool thing about this structure is that it can act like a sponge for oxygen. It can absorb oxygen atoms or lose them, and this flexibility is the key to everything. It's like this amazing domino effect. By very carefully controlling the exact number of oxygen atoms in the crystal, scientists can tweak the distance between copper and oxygen atoms. That little change alters how the entire crystal structure vibrates, and it's those specific vibrations that let electrons team up and flow through with zero resistance. It's all connected. But it is a really delicate balancing act. If you have too few oxygen atoms, the temperature needed for superconductivity just plummets. But when you hit that sweet spot, right around 7 oxygen atoms for each little crystal unit, the performance is perfect. It's like tuning an old radio dial to get the station just right. Okay, so the science is fascinating, but how do you actually build something useful with this stuff? That brings us to the huge engineering challenge of actually making these materials. To make things like wires or circuits, you need to create these super thin films of the ceramic. And here's the funny part. To get a material to work at incredibly cold temperatures, you first have to bake it at incredibly hot temperatures. We're talking up to 950 degrees Celsius. That's the only way to lock in that perfect amount of oxygen. And you can't just grow this film on any old surface. The foundation it sits on, the substrate, has to be a total beast. It needs to handle that blistering heat without melting or reacting. It can't fall apart when exposed to all that oxygen. And it has to prevent atoms from wandering between the film and the substrate, which would just ruin everything. It's an incredibly demanding checklist. So, after all of that amazing science and incredibly difficult engineering, what's the payoff? Was it all worth it? Well, this is where it gets really good. Let's look at a key measurement: critical current density. Basically, how much electrical traffic can the superhighway handle before it breaks down? At a frigid 4 Kelvin, a classic superconductor is amazing. It can handle 10 million amps per square centimeter. But check this out. Even at the much, much warmer 77 Kelvin, the high temp version still handles over a million amps. That is a massive amount of power, but achieved at a temperature that's nearly 20 times warmer and dramatically cheaper to maintain. So let's just sum up this whole story. We went from mercury, needing ridiculously expensive liquid helium near absolute zero, to YBCO ceramic, which works just fine in cheap, everyday liquid nitrogen. The practicality just shot through the roof, opening the door for applications that were pure science fiction before. And that leaves us with the big, exciting question. For decades, the huge barrier for this tech was temperature. Now that we've lowered that barrier so dramatically, the question isn't if we can use it anymore. The question is, what amazing things are we going to build with it first?